Okay, welcome back again. This is going to be part number 8 of collective communications in MPI. So we're going to continue from where we left off in the previous part. We were talking briefly about this MPI scatter. We said it's the cousin of basically MPI reduced scatter block. And the difference between the two is that MPI reduces scatter uses sort of different sizes of blocks that you can receive, or each process can receive. And that is why here we have an array of receive counts. In the case of MPI reduced scatter block, every block has the same size. This is what we said. We essentially have the same stuff, so we're not going to comment on these stuff because we already know the semantics of MPI reduced scatter block. It's going to be the same also in the case of MPI reduced scatter, but with the only difference that we said that the receive counts can be different, and they can be basically populated based on populated in an array based on how many elements you want to receive. And we're going to see examples in both intra and intercommunicator scenarios where we have group A and B in intercommunicator scenarios. So let's jump into MPI reduce scatter.c. We have the same drill here. Everything is the same. But in this case, we have our buffer is a multiple of 4, receive buffer is 4, and receive count is 4. And we populate the send buffer with, again, combination of rank and using the loop counter. And in this case, we also want to have receive counts to be 4. So that is because we had 4 elements, we put the 4 values. So again, this is having the same block size for every receive count, but you can have different sort of sizes as well. But in our case, we are having the same size of receive counts for every block, let's say. And then we are using MPI reduces scatter with the same, more or less the same arguments. Again, MPI sum we are using, and then finally every process basically prints its own results. So let's go with MPI CC, MPI reduce scatter. And doing that, again, starting from process 0, it's going to be 6. And then in the next one, it's going to be plus 4. It's going to be 10. And then plus 4, 14, plus 4, 18. And it goes all the way down to process number 3. And notice that every process gets 4 buffers. And process number 1 also gets 4. Process number 2 also gets 4. And process number 3 also gets 4. So in this case, we used MPI reduces scatter in a scenario that everybody gets the same amount of received buffers. But it could be also different. Now taking a look, this is the semantics of what happens. We saw that reduction happens, and then the scatter happens based on the rank of every process, but the size can be different. Order is always based on the rank. So that is why always process 0 has the lowest value when we are using this MPI sum. But as I said, the count can be different. That's why we have this receive count array. Now let's take a look at MPI reduce scatter inter, which is the intercommunicator scenario. We're not going to comment on these again. In this case, send buffer, receive buffer, and receive count, all of them are going to be pointers. And group A and group B, they're going to populate that. So they're going to allocate their own space with malloc. Send buffer, receive buffer, and receive count in group A must be based on the size of group B. And in group B must be with respect to the size of group A. That is the only significance when you are having an intercommunicator case. Everything else is the same. We are initializing with a combination of rank and the loop process, and the receive counts also must be sort of consistent with the size of group B, and that is why we have the size of group B. And the receive counts for group B is going to be the size of group A. That is super important. And another significant sort of difference is that here, instead of using MPI COM world, we are using the intercommunicator. Everything else basically stays the same. And since in this example we are using malloc to allocate the proper sizing for send buffer, receive buffer, and receive count, of course you have to free all those resources. And then after doing this blocking call of reduce scatter, then basically group A, that's color 0, they're going to print their own results, and group B is going to print their own results as well. So let's do an MPI CC, MPI reduce scatter intercommunicator, and then running with 4 processes. You see that process number 0 starts with 5. Again, group B has processes 2 and 3. You see that the summation is going to be 5 and then 7. You have already seen this. And on group B, they start with 1 because process 0 and 1, summation of 0 and 1 is going to be 1. Then plus 2, you know the drill basically. It's the same. Okay, the next thing is inclusive scan. It takes these arguments, send buffer, receive buffer, count, data type, operation, communicator, more or less the same arguments that we have so far already. And receive buffer is going to be the out. Everything else is going to be the in. So if communicator is an intercommunicator, MPI scan is used to perform a prefix reduction on data distributed across the group. The operation returns in the receive buffer of the MPI process with rank I the reduction of the values and the send buffers of MPI processes with ranks 0 all the way up to I, inclusive I. So that is important. So this operation is invalid for intercommunicator. That is also very important. We're going to take a look at the example. So we're going to have MPI. What was the example? The name of the example was MPI scan. Very, very simple example. These things you already know. We have a send buffer, which is going to get populated with the rank of the process. We have the receive buffer, which is not initialized because we're going to do a scan on it. And this is an inclusive scan. So we pass in the send buffer, we pass in the receive buffer, we pass in the count, we can pass in the type, we pass in the operation that we want to do. That's the summation. And this is in the context of intracommunicator. And then every process basically prints this thing here. So let's do an MPI CC. Very simple example. But it basically shows the semantics of MPI scan so nicely. You can take a look at this. For prefix, this is a prefix sum, by the way. So the send buffer for process number 0, we initialize with the rank, if you remember. So process number 0 has value 0. The scan operation is going to return 0 because that's a summation. Process number 1 is going to it has the value of rank in the send buffer, which is 1. The prefix summation is going to be 0 plus 1, which is going to be 1. Process number 2, in the send buffer, it's going to have the value of 2. But then we already have a 1 here. And plus 2 is going to be 3. That's a prefix sum. Inclusive. So why we say it's an inclusive scan? Because it includes the process, the ith process also as well. Process number 3 has value of 3 in the send buffer, but then we already have a 3 here, and plus this 3 is going to be 6. That is inclusive scan. The counterpart, let's say, is an exclusive scan. Again, exclusive scan, you cannot use it in terms of in intercommunicator scenarios. And it also mentions that it should be an intra-communicator for the communicator here. Again, we have another example for this one. We're not going to talk about what we see there because the example is going to basically show you the semantics. This is how the syntax looks like. Again, the drill is the same. You have the send buffer, which is going to get initialized with sort of the rank of every process. But exclusive scan is very important in the sense that the semantics of this one is that it doesn't include the current process. So that is why I put here rank not equal to 0, because accessing the value of the receive buffer in process number 0 is going to have an undefined behavior because this is an exclusive scan. You're going to see in a second what I mean by that. MPI X scan MPI run. Process 0, I said, if you access that, you're going to end up with undefined behavior because it's an exclusive scan. Process number 1, it has the value of 1. Prefix sum is going to be excluding process number 1 because the buffer in process number 1 has the send buffer of 1. But excluding sum, we are performing MPI sum. Excluding sum is going to only contain this value of send buffer in process 0. Process number 2 is going to have the value of 2 in the send buffer, but it's excluding that value of 2. Summation of 0 and 1 from process 1 is going to be 1. So that is why process number 2 has the value of prefix sum of 1. Again, consequently, process number 3 is going to have the send buffer of 3, but a prefix sum, an exclusive scan, is going to contain the value of 1 and 2, which was in the process, the value of process number 2, and the summation of all those values, value of 0, 1, and 2, is going to be 3. That is why we have these different values. On contrast, we had, for example, for MPI scan, we had 0, 1, 3, and 6, which finally ended up adding all the values in the ranks. But here we go all the way up to value of 3 for the summation. Okay. So we already talked about the semantics. We have seen our own examples. Now we have our non-blocking collective operations. So from this part all the way down, it's going to be very simple because the examples are in consistency with what we had in blocking communication. So we in the first 5 parts of collective communication, we have taken a look at all these examples. I think we had 23 examples. So we're going to have exactly 23 examples. So these are going to be the non-blocking counterparts of the blocking collective communications, which are all in this directory that I have here. Oops. By the way, maybe it's also nice to talk about this one. You see that I have a safety check, sort of a bash script here. And that is why, while I was writing these examples, I usually make like trillions of examples. And you should pray to God that you get, once you are basically using this MPI library, either it's going to be MPeach or the one that is done by OpenMPI, you should pray to God that you get an error if something goes wrong. Because if you don't get an error, sometimes, the processes are running behind the scenes. And once you say jobs, then you get no basically process, no jobs running. So jobs doesn't help you to show you those processes which are running in the background. So it happened to me that I did a terrible mistake when I was preparing one of these examples, and then those basically processes were running in the background, and then I saw my laptop, the battery was getting drained all the way to 0, and then I was the fan was working, and I was what is going on? And then I checked my activity manager, and then I saw that these a.out processes are running in the background, and I didn't know that because I was checking with jobs, and then I saw that so the thing that I have in this safety check is simply that I'm using all the processes that are running, and then I try to grab this a.out. That's usually the output I use, the default output of MPI-CC, and I use awk to print sort of the second thing here to get the sort of the process ID, and then I try to kill that process. So and then while I was, let's say, developing the other examples for you guys, then I was always doing this safety check to make sure that if I have made a mistake and something is running in the background, I need to kill them. Okay, this was let's say, a funny story about that. But we're going to now start with non-blocking collective operations. As described in section 3.7, performance of many applications can be improved by overlapping communication and computation. This is the whole idea of non-blocking communications in general, and many systems enable this. Non-blocking collective operations combine the potential benefits of non-blocking point-to-point operations to exploit overlap and to avoid synchronization with the optimized implementation and message scheduling provided by collective operations. You can take a look at references 35 and 39. One way of doing this would be to perform a blocking collective operation in a separate thread. An alternative mechanism that often leads to better performance, avoids context switching, scheduler overheads, and thread management is to use non-blocking collective communications. Take a look at the reference number 37 if you're interested. The non-blocking collective communication model is similar to the model used for non-blocking point-to-point communication. We have a consistency here. A non-blocking call initiates a collective operation which must be completed in a separate completion call. This is very, very similar to non-blocking point-to-point communications that you initiate the communication operation, but then you have to always make a completion call with MPI test and MPI wait. It's the same story with non-blocking collective operations. Once initiated, the operation may progress independently of any computation or other communications at participating MPI processes. In this manner, non-blocking collective operations can mitigate possible synchronization or synchronizing effect of collective operations by running them in the background. In addition to enabling communication computation overlap, non-blocking collective operations can perform collective operation on overlapping communicators, which would lead to deadlocks with blocking operations. So this is also very important. If you have overlapping communicators, like in the cases, we haven't talked about these communicators, but overlapping communicators means that if you have communicator A, which has processes 0, 1, 2, 3, and you have communicator B, which has processes 2, 3, and 4. You know, in group A, you have 0, 1, 2, 3. So 2 and 3 are overlapping in group B as well, because group B has 2, 3, 4, and 5 processes. So that is the context. If you use blocking sort of collective communications, you have the possibility of having deadlocks. You would end up having deadlocks in your collective communications, but with non-blocking versions, this is getting mitigated basically. As in the non-blocking point-to-point case, all calls are local and they return immediately, irrespective of the status of the other MPI processes. This is also very important. Then we go here, it says the call returns a request handle which must be passed to a completion call. This is also super important. One of the differences of non-blocking communication calls in general is that it works with a request handle, that you can pass that request handle to an MPI test and MPI wait to query basically what is the status of communication. All completion calls, something like MPI wait described in section 3.73, are supported for non-blocking collective operations. Similarly, to the blocking case, non-blocking collective operations are considered to be complete when the local part of the operation is finished. For example, for the caller, the semantics of the operation are guaranteed and all buffers can be safely accessed and modified. So that is okay. Completion also doesn't indicate that other MPI processes have completed or even started the operation, unless otherwise it is implied by the description of the operation that you are working on. Completion of a particular non-blocking collective operation also doesn't indicate completion of any other posted non-blocking collective or send receive operations, whether they are posted before or after completed operation. Upon returning from a completion call in which a non-blocking collective operation completes, the values of the MPI source and MPI tag fields in the associated status object, if any, are undefined. The value of MPI error may be defined if appropriate according to the specification section 3.2.5. The rest is probably we should not spend. Okay, one thing is important is that it is erroneous to call MPI request free or MPI cancel for a request associated with a non-blocking collective operation. That is important. Um, because you know that non-blocking communications, the request free is usually done for persistent calls, because we know that inherently blocking and non-blocking sort of communications, they take care of freeing resources. But once you're working with persistent communications and partition communications, nobody's taking care of those freeing of resources. You have to explicitly say MPI request free. You need to explicitly free the resources that you're using. Okay, so I think we should not spend too much time here, because you know the semantics are going to be similar to what we have in blocking ones, but have this in mind that we have already this background of blocking and non-blocking communications. What was the semantics of non-blocking ones? That the call returns immediately, and then you need to query for completion of the communication. And this is exactly the same drill also for collective communications in non-blocking sort of type. Here it says that unlike point-to-point operations, non-blocking collective operations do not match with blocking collective operations. And collective, so you know you can match, for example, non-blocking send with a blocking receive, but here you cannot match non-blocking collective operations with blocking collective operations, and collective operations do not have a tag argument as well. Okay, so in terms of data movement, each non-blocking collective operation has the same effect as its blocking counterpart for intercommunicator and intercommunicators after completion. So I'm going to go like blazing fast through these examples, because we're going to have billions of examples ahead of us. And you have already seen the syntaxes and semantics of the blocking ones, and you have already seen in detail the syntaxes and semantics of reduce operations. So from this section onwards, we're going to talk about all the non-blocking collective communication operations, plus non-blocking reduction operations, plus persistent collective communication operations, plus persistent reduction operations. So these are all the sections that we want to take a look at, but we're going to go, as I said, blazing fast, because we have already seen the counterparts in blocking sort of collective communications and in blocking reduction operations. So if it's too fast for you, please go back and watch the parts prior to this part, all of them, for blocking and reduction collective operations or communications. Okay, the first one is MPI I barrier. That's MPI I barrier example. So vim MPI I barrier. .c. I'm just going to show you so that you can pause the video and take a look at this one, but we're not going to spend too much time on this. So this is simply a barrier, but this time is a sort of non-blocking call, and I intentionally put the wait here so that this can be executed. So because the what's it called, the blocking call happens here. This MPI wait is the blocking call, and it happens after this statement. So you can see hello and bye without basically having this synchronization that hellos are going to get printed first and then byes are going to get printed. So MPI CC, MPI I barrier, .c, MPI run. In this case, I don't know what mpeach does, but somehow if you run it multiple times, oh yeah, so it's not always the case. So you can have cases that bye happens after hello, but this one was sort of very perfect. It gives you those ideas that, hey, is there any synchronization happening here? Whoops. So we already managed 25 minutes here. We're gonna go to the next part to continue this this non-blocking collective communications.